Hello. In this video, we will look at the problem to find the shortest path between every pair of vertices in a graph. We will apply the dynamic programming approach to solve this problem. Now, we are going to use an algorithm called Floyd Warshall algorithm to solve this problem using the dynamic programming approach. Here we will take this graph as an example for understanding of this algorithm. This particular graph has four vertices: vertex 1, vertex 2, vertex 3 and vertex 4. As we can see that the vertex 1 and vertex 2 are connected by an edge which has a weight of 1, and between the vertex 4 and vertex 3 there is an edge which has a weight of 4, and so on. Here in this example we have to find the shortest distance between vertex 1 and vertex 2, vertex 1 and vertex 3, vertex 1 and vertex 4. Similarly, we will find the shortest distance between vertex 2 and vertex 1, vertex 2 and vertex 3, vertex 2 and vertex 4, and so on. Now the shortest distance can be like a direct edge, like here it can be a direct edge between 1 and 2, or it can be through an intermediate vertex, suppose 3. So the shortest distance can either be a direct edge or it can be through an intermediate vertex or vertices. So as discussed, besides checking for the direct edges, we have to also check for the distance via an intermediate vertex or vertices. So the approach will be to first select the vertex as an intermediate and then check for the shortest distance for pair of vertices. And, and then after that select the second vertex as an intermediate and do the same. Continue this till all the n vertices are taken as intermediate and shortest distance will be calculated. So first we are going to get an adjacency matrix of size n cross n, where n is the number of vertices. In our case, we are going to create a adjacency matrix of size 4 cross 4. Now to fill this adjacency matrix, first of all we are going to fill the diagonal elements with value 0, because no self loop is allowed here. It is 0, it is 0 and it is 0. Now for the rest of the elements we are going to fill them with the value that corresponds to the direct edge weight, like between vertex 1 and vertex 3 there exists a direct edge whose weight is 3. Now for those pair of vertices which do not have a direct edge, like between vertex 4 and vertex 1 there is no direct edge, we are going to fill this list by infinity, and we are going to name this matrix as A0. As discussed earlier, we will consider vertex 1 as our intermediate. Now we will generate the matrix A1 and will keep the first row and first column same of the matrix A0, and we are going to put them as it is in our matrix A1. Now for the rest of the elements we are going to generate them. Now we are going to fill all the diagonal elements of A1 0, because no self loop is allowed. It is 0, it is 0 and it is 0. Now we are going to calculate element A1 2, 3, and we will check that whether a shortest path exists if we take 1 as an intermediate or not. So for that we are going to take the minimum of A02, 3 and A02, 1 plus A01, 3, and whatever be the minimum will be taken as the value and filled in the matrix A1. Here this comes out to be, here this comes out to infinity, so we are going to put it infinity. Now we are going to do the same procedure for A1 2, 4. Now for A1 2, 4 we are going to consider intermediate as 1. Here A02, 4, here the value of the A02, 4 is 4, and now if we consider 1 as the intermediate, this value becomes infinity. So hence the minimum of these two, which is 4, is going to be inserted in this matrix. For element A1 3, 2 the value of A0 3, 2 is 4, and now if we consider 1 as the intermediate, this value becomes 3. So the minimum of these two values, which is 3, will be placed in the matrix. Now for element A1 3, 4 the value is A0, the value of the A0 3, 4 is infinity, and if we take 1 as the intermediate, the value still is infinity, so we are going to place infinity as it is in this place in the matrix. Now using the same concept as we have discussed previously, we are going to fill the last row of our matrix A1. Now we will consider vertex 2 as our intermediate and we will generate the matrix A2. We are going to keep the elements of the second row and the second column of the matrix A1 as same, and we are going to put them in the matrix A2 as it is, and for the rest of the elements we are going to calculate them. Now first of all we are going to fill the diagonal elements of this matrix A2 with 0 because no self loops are allowed. Then we are going to first of all fill the element A2 1, 3. We are going to check if a shorter path exists if we take 2 as an intermediate. Here the minimum value is 3, so 3 is placed here. For A2 1, 4 we are also going to check if a shorter path exists if we take 2 as an intermediate. Here the minimum comes out to be 5, so 5 is going to be placed here in this matrix. For element A2 3, 1 we are going to use the same logic as used previously, and we find that the minimum value is 2 and we are going to place it in the matrix. For A2 3, 4 again using the same logic we find the minimum value is 7 and we are going to place it here in the this matrix A2. Now using the same approach we are going to fill this last row of our matrix A2. Now we are going to consider vertex 3 as our intermediate and keep the elements of the third row and third column same in the matrix A2. And now we are going to generate a matrix A3, and first of all we are going to put the elements of these third row and third column as it is in this matrix, and we are going to continue to generate the elements as we did in case of the previous matrices A1 and A2, and this would be our final matrix A3. Now similarly we are going to take our fourth vertex as an intermediate and we are going to generate the matrix A4 by keeping the elements of the fourth row and the fourth column same of matrix A3. Now as in our example there were only 4 vertices in all, so we are going to stop, and this final matrix A4 represents the shortest distance between the pair of vertices. Like for example, if we have to find the shortest distance between the vertex 2 and vertex 3, it is going to be 8. If we have to find the shortest distance between vertex 4 and vertex 2, it will be 6. And if we have to find the shortest distance between vertex 3 and vertex 1, it would be 2. The generalized formula of our approach: let there be a graph with n vertices numbered from 1 to n and Ax be a matrix. Then any element in this matrix, let's say Axi, j, can be determined by finding the minimum between Ax minus 1 I, j and Ax minus 1 I, x plus Ax minus 1 x, j. And whatever be the minimum of these two values is going to be considered for this element. The value of x here ranges from 1 to n, and if x equals to n, then we can say that we have reached our final matrix. Now during this implementation of this algorithm we are not going to create n different matrices, but instead we are going to modify our initial matrix A0, and we are going to modify this A0 to A1, and this A1 to then A2, and then so on. Here in the previous example, we are not going to create 4 different matrices, but instead we are going to convert our initial matrix, which was A0, to A1, and then we are going to convert this matrix A1 into A2, and we are going to then convert this matrix A2 into A3, and after finally we are going to convert this A3 matrix into A4, and this A4 matrix, and this matrix A4 will represent our solution. Now the space complexity. To find the space complexity of this Floyd Warshall algorithm, first of all, we are required to create our initial matrix adjacency matrix A0, and to do that we have to create a matrix of dimensions n cross n, where n is the number of vertices. Hence we can say that the space complexity is big O of v square. If our vertex is equals to, if the number of vertex is n, then we can say that the space complexity is also big O of n square. Now the time complexity of the Floyd Warshall algorithm, as we have to generate subsequent matrices using this formula. So for this we have to access every element of the matrix, and to do that we would need two for loops, this for loop and this for loop, and because of these two for loops we will be able to access each and every element of the matrix. Besides accessing every element of the matrix, we are also going to require another loop so that we can iterate through the values of x from 1 to n. And when the value of x reaches to the n, we can say that we have found the answer. So as we have seen that this algorithm requires at least three for loops, so we can say that time complexity of this given algorithm is big O of VQ, where V is the number of vertices. If the vertices equals to n, then we can say that the time complexity is big O of n cube. So with this, it concludes our discussion of the Floyd Warshall algorithm. Thank you.